Hi, this is Samantha Scott. I'm doing the video portion for Calculus 1 Test 3 Part 1 Take Home. So I'm going to start with question number 1. So you asked to have a graph, to consider the graph of a function that has the properties listed below, that the first derivative has the f derivative of x is equal to 0 when x is equal to -3 and x is equal to 5. So whenever the first derivative is equal to 0, it means that it has a slope of 0, which means that when the tangent line hits it, it's at a completely flat line. So I have a paper of what just like a graph of that would look like. And so if we look at the fact that x equals -3 and x equals 5, that means that that when x is equal to -3 and x is equal to 5, it has a slope of -0. -0 of 0. 0 is neither positive nor negative. I'm sorry. So I chose this graph just because since we didn't have an actual equation, I just chose one. So since the slope can either be at the top, so I chose for when x is equal to -3, it's at the top, so the slope is still 0, and then when x is equal to 5, the slope is 0. And then if we take the derivative of that, basically if we take the first derivative of that, oh, and just to mention, whenever the first derivative is equal to 0, those points are critical points. So in this case, the critical points of this graph would be x is equal to -3 and x is equal to 5. So if we graph if we graph the first derivative, we end up getting this. It also has one less bump than the original, which is what happens when you take a derivative. And so when x is at 0, when it's at x is equal to 3 and x is equal to 5, if you take a look at the top, forgive me, this is a little disorganized. So the slope approaching -3 is positive, so it is in the positive for -3, and then the slope going from 5 is also positive. So when I come down here, it's also, there we go, everything's backwards. It's also 5. And then from between -3 and 5, the slope is actually negative. And so between 3 and 5, this actually passes into the -y because the fact it's a negative slope. Now during that, you also ask for the point of inflection. Point of inflection is when the second derivative is equal to 0, which due to point B, the second derivative is when x is equal to 1. So that point when graphed is actually this point right here, where the little arrow is. It's the point when it starts approaching the positive. So that's also on here, it'd be like right around here. So when you take the derivative of that function, it ends up looking like this. There we go. So the point of inflection is where f of x, graphically, it's when the point changes, also when the second derivative is equal to 0. So, and then you say that the second derivatives are as follows, there we go. Graphically, when it is in the positive, when it's like at 0.3, and then it reaches the point of inflection right here, which is where it hits 0, when the direction changes. And so then once it's at positive 5, it is now on the negative. So in order to to put it on the actual paper, I graphed this, like the first thing. And then I put The relative max being at -3 because it's the highest point on the graph, and because when you would, well, there's no number, so I'm just going to leave that there and explain it for the second problem. And then it's also a critical point because x is equal to 0, and I kind of put a tangent line just to show that the slope is 0. And I put the same one at x is equal to 0. Yes, x is equal to 0 because it is also at 5, which is a critical point. It's also a relative minimum because it is the relative minimum of that part of the problem, that it is the minimum. And then the point of inflection, it's at 1. That's what that dot is. It also is point of inflection. Okay. So I think that's all I can kind of explain for problem 1. To move on to problem 2, I know I don't have any of the writing right here, which I'm going to fill out after this video. However, I do have the graph. I'll explain that in a minute. I do have all the work on this other sheet of paper because I write big, usually. It helps me with math. And so I wrote down the original equation, which is 2x to the third minus 3x to the second minus 36x plus 7. So I'm just going to show the first part. So in order to take the derivative of that, it's 6x to the second minus 6x minus 36, and we set that to 0, which is what I did. I pulled out a 6 and then kind of pulled it apart, like unfoiled, which I factored it. And so it's 6 times x minus 3 times x plus 2, and set that equal to 0, which means that the when you solve it, x is equal to 0, -2, and 3. And so I ended up putting that back into the problem, and I used the -2 and the 3. And so when you just plug that back into the original problem, and so you end up getting 51 when you put in a -2, which means as a point, it would be as in x, y, because that is because A says to determine 2 critical points in the form of x and y. So since I put in a -2 and got out of 51 in XY format, that is -2 and -2, 51. And then when I do that with a 3, I get out of -74. So it's 3, -74 in XY format. To move on to part B, use the second derivative test to determine whether each critical point is a local maximum or a local minimum. Here's B. I'm really sorry, this is very much backwards. So when you take the first derivative, which is 6x squared minus 6x minus 36, you take the derivative of that, which ends up being 12x minus 6. If you so for the -2, which I plugged in here, I plugged in here. So 12 times -2 minus 6 is equal to -30. And then when you plug in a 3, you get +30. Now, when you take maximum and minimums, according to my textbook and to practices, when the number is negative, that means it's the maximum. And when it is the positive number, it's the minimum. This is also what my tutor told me. I don't understand the theory behind it. I've just come to accept it. So that is about as much explanation as I can give to that. So the -2, 51 is our maximum, and the 3, -74 is our minimum. So part C is evaluate the second derivative in order to determine one point of inflection in the form of xy, which is what this is. So basically you take the second derivative, which is 12x minus 6 equals 0, and you solve for x, which ends up being 1/2. You plug that back into the first derivative. So when you plug that into 6x to the second minus 6x minus 36, you end up getting -37.5, which you said that you like everything in fractions. So I chose to adhere to that, and I got -75 halves. So in XY format, that is 1/2 negative 75/2. So that is the point of inflection. Yes, that is the point of inflection. And right here, I made a little note. Right here. Point of inflection is when the second derivative is equal to 0. That is when it's equal to 0. So at that point, for D, it says use your graphing calculator to display the function in an appropriate window. So when I chose to do zoom fit, it didn't work. So I chose to put in, I put in the original function, which is 2x to the third minus 3x squared minus 36x plus 7. And when the zoom fit, which is zoom button 0, did not work, I put in my x min is -5, my x max is 5, and I scale that to 1. And then with the y, since it's very large numbers, I chose to go down to -75, go up to 55, since one of the points is 51, and chose to scale that for every 25. And when I press, there we go, graph, I get that. And so it shows that at -2, 51 is our max, and 3, -74 is our min. So that's proven. And so I put this on my sheet. Here we go. So it looks the same, sort of, as much as I can do freehand. So, but I know the numbers, and I can transfer on this in like a second. But I needed the numbers to be large enough so that I could read them. So for part 3 is the written part, which I will be posting onto Moodle in a few minutes. And I wrote those on a separate sheet of paper as well because, again, I write big and I needed more space. So I will be posting that. However, I have the original problem on them as well. So thank you so much. I hope I explained everything well, and have a great day.